Yeah, I'll be I'm discussing something just about outline of the assignment. So I think something in that direction will get covered. So let me
Okay,
share
sir.
my. Okay, so before I get on to this, let me spend some time on VHDL guidelines. What I notice is that many of you have difficulty in using VHDL, and I can understand that you haven't gone through practical experience with that in the last semester. So some instructions are actually in order. One often thinks that if you know programming and you pick up the syntax of VHDL, that's good enough. Okay, so trying to think of VHDL as just another language to code, and one tends to think directly in terms of VHDL construct. So if statement, there are loops also, various things are there, and you start thinking in terms of those. And thinking that any syntactically valid VHDL description is fine. So, and you expect the tools to make correct sense out of it. So all these are actually not correct. Okay. So this is a point I want to drive home clearly, that do not think of just VHDL as another way of programming. What you need to do is you need to think in terms of circuit structure first. Okay. Whether you are designing a combinational circuit or sequential circuit, what kind of circuit it is. So you have to visualize that circuit at some abstract level, not necessarily at the level of gate details, but in terms of nature of the circuit, and then try to describe that in VHDL. So I think your thinking should not start with VHDL. Thinking should start with what is the circuit you want to describe. It's advisable to use some well understood abstractions. Okay, so some templates in VHDL should be used. Don't try to write VHDL code in arbitrary manner. Okay, so there are a few specific ways of describing specific things, and you must stick to that, because uh, particularly synthesizer tool would expect things to be written in a certain way. Okay, so anything you write in VHDL which passes syntactic test is not necessarily correct. Okay, so you should not lose the sight of underlying hardware. These are the correct ways of going about it. And the in terms of design style, an architecture can have components which are instantiated, components which are defined separately and instantiated in your in a new component, a new entity which you are defining. So that is essentially a structured description. Or you can, yeah, we get some disturbance somewhere. Uh, your mic, please.
So you could mute everyone. So you could mute everybody once.
Uh, I think it is Sai Ram Nayak.
No, it's Bali side.
Huh? I don't want to mute everyone, because I like you to ask questions whenever you want. So
No, sir,
that
if
You
you
get
mute
the option to
everybody,
mute for once.
yeah,
Like we want to be muted
yeah, if you mute
also,
everybody,
but
then
for
we
now
would
you
be able to
mute all the
unmute
time.
ourselves.
okay.
I think it's in the participant topic.
Okay. Mute all. Okay, that's better now. So a design uh, could be having structural components in the form of instances of components. It could have processes which describe procedural flow of control, and you could have some. Just 1 minute. Let me get the laser pointer. Yeah, you could have concurrent assignments which represent data flow.
Yes.
Yes, question?
Yes, sir. So one thing I had a doubt. So when we have a process with the various inputs inside in sensitivity list, how is it different from concurrent assignment?
Okay, I'll come to that in a moment. So concurrent assignments are typically used to describe combinational circuit, and processes could be used for either. Okay, depends upon how processes are used. You could use a process to describe combinational circuit and as well as sequential circuit. So what would distinguish between the two? I'll come to that shortly. Uh, so in general, you can mix the two. Within a given architecture, you can have a combination of these. It is quite possible as long as you clearly understand what is happening. But if you keep these separate, separate out structure from uh, behavior, the description is cleaner. Okay, but it's understandable that uh, giving structural description is very tedious. You need to create entity, then create an instance, pass define signals, pass them on. So there's a lot of writing work to do. It becomes tedious, although it clearly separates out different pieces of logic, but it's somewhat tedious. So the approach I'm advising you is a mixture. That is, you're mixing these things. Okay, but one must be conscious of what part is used for what purpose. So if you look at the entire design, you would typically have a structural hierarchy, that is a large component consisting of smaller components, so on. And in that hierarchy tree, at the bottom you have behaviors. Okay, so ultimately everything is described in terms of behavior, which is from a semantic point of view considered as a process. Okay, so at the bottom you have behavioral descriptions. Let me now talk of different types of circuits. We have combinational and sequential. Sequential circuits could be asynchronous or synchronous. So synchronous circuits means they are driven by clock. The values change at the particular clock edge. Okay. In asynchronous circuits, the signal values can change in response to change of any signal. So obviously combination circuits have no storage of memory, and they react instantly to change in inputs. Okay, so this statement about instantaneous reaction is only notional. In practice, the combinational circuits would have certain delay. Okay, but as long as the delay is within a clock period, so let us say you have combinational circuit driving input of a register. So as long as the delay is less than a clock uh, period, then it's as good as instantaneous reaction. Okay, so given a
Excuse me,
clock,
sir.
you should keep your delays which are less than the clock period, or if you're deciding the clock period, it should be sufficient to allow for signals to propagate through combinational circuits. Yes, there was a question.
Sir, here the delay in the combination circuits. Let's say I perform something, like evaluate something through combination circuits, and
Yeah.
that is again needed in something else. right? And it is within the same clock period.
Yeah.
So the entire delay should be less than, right? So the combination of circuits delay we might want that to be much lesser than the clock period, right?
Yeah. So you may have several pieces of combinational circuit going from, let us say, some registers to the next set of registers. The combinational circuit path may include several pieces which we may have defined separately. So it is the delay of entire path which is of concern.
Okay.
Now, when you are writing description, when you're doing design, you don't know what these delays are. Okay, you are not explicitly specifying any delay. So typically, what happens is that synthesizer, when it figures out which components are actually going to implement your design, it knows what the delays are, and then it can tell you that yes, this design which you have done, it can be clocked with a frequency which has to be less than equal to this value. Okay, so it can analyze the delays in various paths and tell you what is the fastest clock you can run. Okay, so right now our focus is not on those aspects. Okay, our focus in this exercise is more on understanding the functionality and describing that, and not so much about delays and frequencies. Okay, now sequential circuits, whether you have asynchronous or synchronous, they have storage, they have memory. Asynchronous circuits are level sensitive, whereas synchronous circuits are edge triggered or edge sensitive. Uh, so we recommend that you use combinational circuit and avoid asynchronous sequential circuits. Okay, these are hard to design and analyze and can lead to very unexpected problems. So your design should be all, the sequential part should be all synchronous, and that could be coupled together with combinational circuits. So sometime in your attempt to write combinational circuits, by inadvertently, it may turn out to be an asynchronous sequential circuit. So I'll come to that, and that is a dangerous part which has to be avoided. So combinational circuits, if you are using concurrent statements, there should not be any cycle. Okay, there should not be any cyclic dependence. That is, if you write A equal to B and C, and C is defined in terms of something else, and then again there is a dependence back on A. So if there is a cyclic dependence among signals which are driven by combinational circuits or concurrent assignments, then there'll be a problem. So that it will no longer be combinational circuits. So in VHDL, every signal that is destination of some assignment should get assigned under all conditions. I mean, if you want the circuit to be combinational, then there should not be any memory. So if you are making assignment to a signal under certain conditions, you must make sure that under all conditions something gets assigned. So if you're using selected signal assignment or conditional signal assignment, then the last catch-all clause must be there. Okay. Otherwise, the way it gets interpreted, if under some condition it is not assigned, is that the old value holds, and immediately it means that there is some storage. Okay, if under certain condition a signal is not assigned in value, implication is that the old value is supposed to continue, and that clearly implies storage, and it actually leads to the synthesizer will interpret this as an asynchronous sequential circuit. Okay. You can use a process also to describe combinational circuit. Uh, you have to make it sensitive to all the sources. So within the process, all expressions which you have in the right hand side of assignments, or all expressions which you have in, let's say, in case or if then else statements, so anything which you're reading, anything which is input to this process must be sensitive to all. And again, for all possible conditions, the destination should be assigned some value. So all these conditions must hold if you're describing a combinational circuit, and any slip on this actually takes it into a wrong direction.
Sir?
Yeah.
So suppose I have a process where I have all the inputs in its sensitivity list. Then I define a signal which has to be assigned a value, and then I use that value inside inside the process itself immediately after that.
Yeah.
So here, will the value get the correct answer?
No, you will not get correct answers. So I'll come to that shortly.
Okay.
Yeah. So that is
Excuse
another.
me, sir.
It's coming in one of the later slides. Yeah.
Sir, in the second point, here the signal refers to local signal of the process, right? Like signals which we define within the architecture.
Within a process, inside process, you can't define signals.
Oh, sorry.
Yeah, signals are outside the process.
Okay.
Okay. So in an architecture, there can be one or more processes. The signals have to be defined at the architecture level.
No, like I'm saying, like sometimes there are some signals which we take input, like input ports, output ports, and some signals which we define within the architecture, like kind of local signals to that architecture, right? So here the signal refers to those architecture signals, right?
Yeah, so a process can make an assignment to a local signal and also to an output port. Okay.
Yeah, okay, fine.
Yeah. So now, like a signal, you should decide whether the output port is to be driven by combinational circuit or a sequential circuit. So if you want a combinational circuit to drive an output port or a local signal, you have to follow all these. Okay. So moment you violate, you end up in a sequential circuit, and this may be not intentional, but any slip will actually lead to this and cause a lot of problems. So if there is a cyclic dependence or a signal is not assigned in all possible conditions, or process is not made sensitive to all its sources, then it's no longer a combinational circuit.
So the second statement implies that if we have switch case statements which are not exhaustive, we have to at least initialize the signal with some default value.
Yes. Yeah. Well, initialization not in the declaration.
Yes, sir.
In the beginning of process, also you can assign some default values.
Yes, sir. Good.
So from semantic point of view, entire design in VHDL is eventually thought of as a collection of concurrent processes. So even a concurrent assignment is viewed as a concurrent process which is repeating itself. Okay. So processes communicate with each other through signals, and you don't declare any internal signal within a process. Although synthesizer may create some in the process of synthesis, but from description point of view, you don't define any signal within the process. They are outside, and different processes within an architecture can communicate through those signals. Yeah, another question? Okay. So you need to ensure that each signal is driven by only one process. Driving a signal means making an assignment. So if a process is assigning something to a signal, it means it is driving it. All right. And technically speaking, you can have multiple drivers for a signal, but then you need to ensure that there is a resolution function in place and so on. So, for example, if you want to describe a tri-state bus, then you'll have to have possibility of signal being driven by multiple sources. But for the present context, we leave that out, and we have to ensure that each signal is driven by only one process. Okay. So now signals may be going across components as you create instances and you pass signals as actual arguments for the ports. So what is happening is that signals are going across components. So from one component it goes to other component, from there it could be going to another component. There could be nesting of instantiations and so on. So taking everything together, there should be only one process driving any signal. Okay, it may be passing through many components, but there should be only one driver.
Sir?
Yeah.
So one thing, sir, can you go to the previous slide?
Yeah.
The previous one.
Before this?
Yes, sir.
Yeah.
So here the second point in the sequential circuit, if there is some signal that doesn't get assigned, then it gets XXXS I saw in the VHDL, and then it continues to work on that. So would that be why would it convert to a sequential circuit?
Well, as far as simulator is concerned, it will just try to depict the behavior at it. A simulator is not categorizing this as a sequential circuit or a combination circuit.
Synthesizer. Okay.
Yeah. So it will keep on generating values for various signals and show them in waveform. But it is a synthesizer interpret this as
yes,
a combination circuit or sequential circuit. Okay?
Stage I had to change.
Even in simulation, you could get unexpected behavior if your intention was to make a combination circuit, but some rules are not followed. Then sometime the behavior could be unexpected.
Okay.
Okay, so a process is nothing but a repeated computation of values and assignment to signals. Okay, that's all that is happening. A process executes in 0 time. So moment you enter process, all that computation which you are describing actually happens in 0 time. When I say 0 time, it means 0 simulated time. It's also possible to write processes which execute in non-zero time, and that is done by using wait statements. So my recommendation is that use these non-zero time processes only in test benches when you want to assign different values at different points of time. Okay, so you use you assign a value to a signal, then wait for a certain time period, assign next value, and so on. Only for that purpose you use these. Otherwise, for your main design, don't use wait statement. And given that your processes would be executing in 0 time. So whatever complexity it may have, it's all supposed to execute in 0 time. So a 0 time process may represent a combination circuit or a sequential circuit, as I mentioned. And in a sequential circuit, some values may change, some may not change, but in combination circuits, you expect it to make assignment to all values. So it may be the old value you are still assigning, so it may not cause a change in the output, but assignments have to be made. So a signal is either an output of a gate or a flip-flop or an array of these. So in other words, I have already said that a signal is driven by a combination circuit or a sequential circuit. Okay, so accordingly, it's driven by a process of appropriate type, and there should not be any mix-up. So when a synthesizer interprets your circuit as a asynchronous sequential circuit, so it basically creates latches which are level sensitive. Each signal is driven by a unique process, but a process may drive multiple signals, which is quite understandable. So just to repeat, process describing a combination circuit is sensitive to all its inputs, assigns to all outputs under all conditions. A process describing a sequential circuit is sensitive to a clock. We like to restrict ourselves to clocked processes or synchronous sequential circuits. All assignments to outputs are on clock edge. Optionally, you could make it sensitive to additional signals, but use that only for initialization purpose. Okay. Initialization with declaration is good only for simulation. So when a circuit gets synthesized, those initialization which you do in declaration, they are all ignored. So for describing a clock process, I think easiest thing is to follow the D flip-flop template. Okay, so that's the simplest sequential circuit, but even very complex. So here is the example of a D flip-flop with synchronous set reset. Okay, so clock is an input. I'm not showing the entity part and the ports. So basically, clock is an input, and set reset signal S and R are also inputs. So in this case, it is purely synchronous. Even set reset operation initialization will happen with the clock. So if clock is 1 and clock even, or you could say rising edge of clock, then depending upon S and R, you would initialize to 1 or 0. If these signals are not present, then you will initialize to, then you will assign the incoming value D. All right.
Sir,
On
I
the
had
other
a
hand,
doubt.
if you want asynchronous, yeah.
So like if suppose in this case S is also changing on the clock edge. Suppose
Yeah,
S is
so
going from 0 to 1 on the clock edge.
if you say that S or R, they are changing exact, or even D input change exactly at the clock edge, then that's a troublesome condition. Okay, circuit could go into what is called metastable state. So it the voltages may get stuck somewhere between 0 and 1. Right. Usually, what is happening is that in a purely synchronous circuit, the input, let us say D input, is coming from another flip flop. Okay, imagine that. Ignore S and R for the moment. Just the D flip flop. So we are assigning D value to Q at the clock edge, and typically D would change little after the clock edge. So because D would be coming from typically another flip flop. Okay, which will also be triggered by the same clock. So the output of that flip flop would be changing a little bit after the clock edge, okay, corresponding to the output delay of that flip flop. And these signals also may come through some combination circuits, adding further delay. So therefore, typically in a synchronous circuit, it is safe. The inputs change little bit after the clock, and that is good enough. But if an asynchronous input is coming to a flip-flop, then there is a possibility of circuit getting into metastable state. So usually, some signal disturbance can bring them out of metastable state, or after some delay, which may not always be predictable, they would reach a 0 or 1 state. Okay, so those are peculiar circuit conditions. So let's not get digress too much into that.
So sir, like in this
Yeah.
case, if you wanted to remove that problem, that suppose our D is changing on the clock edge. So
Yeah.
like what we could do, like should we shift that D1 a bit before the clock or something like that?
So typically what is done is that if you have asynchronous inputs coming to the circuit, you would put some circuitry at that point to synchronize it. Okay, so we'll not go into details of those synchronizing circuits. So for bulk of the design, you assume that the inputs are synchronous. They're changing after a little bit of delay after the clock. Okay.
So, sir, let's say the ALU that is asynchronous, right? The way we designed, because it is
No,
not
no.
clock.
Let's not say ALU is asynchronous. ALU is combinational circuit.
Then what is the difference between asynchronous and combinational in that sense?
Asynchronous sequential circuit is Okay, the next example. Here set reset operations are asynchronous. Okay, they are happening independent of clock.
Okay, so like, why is it not combinational? What's the
Pardon?
difference? Why is it not combinational? Why can't it say this?
This is still sequential circuit. That means it retains value after the change has gone. Combination circuit have no storage.
Okay, so
And
just because of the third line, it is combinational. Sorry, sequential.
Okay, let me.
Sir, had they been say no clock, then will it be combinational or asynchronous?
Yeah, just let me come out of this and let me change the description slightly, and it will become asynchronous latch. So now suppose I do this. Let's forget about set reset.
Sir?
Yeah, just give me a minute.
Okay.
Clock equal to 1. Let me forget about the edge. Look at this now. So what I'm saying is, if just a minute, clock is 1D1. Yeah, so here if I'm looking at clock level and making an assignment. Okay. Okay, I should let me make it sensitive to D also. So this is asynchronous storage circuit, asynchronous latch. It is level sensitive.
Okay.
While clock is 1, any change in D will be reflected in the output. Okay.
Yes, sir.
So, but if I go back to this and here, even if I make it sensitive to D, any change in D will not affect. The changes will happen only at the clock edge. Okay, so that is the difference.
And sir, could you like with some modification, could you make this combinational also so that it becomes clear the difference?
Make it combinational.
So I think we have to add an else statement, like if clock is 1, then else, otherwise do
Yeah.
this.
So let me remove the edge first of all. Then Q equal to D and else say Q is assigned not of D, something like that. Okay, so under all conditions I'm assigning something. So this will be a combination.
Okay, so in this case, let's say I want to retain the value of Q and nothing else. Like, so what should I do then?
If you want to retain the value of Q,
so in a combination circuit.
No, in combination circuit, you cannot retain the value of Q.
So I'll have to design an asynchronous circuit.
Combination circuits have no memory storage. They will look at all inputs and decide something.
So then, in that case, ALU will be this asynchronous, right? Because there, for some parts, we do not like update the values.
Well, if you have done that for, then you will not. Then it is not ALU should be a combinational circuit. For all in it may give some false values, right? Suppose you have of category dp dt branch and something else which is not defined, or what we have not implemented. Under those conditions, let ALU output all zeros. Okay.
So your voice was lagging. Can you repeat?
So your voice was lagging. Can you repeat everything?
What I'm saying is that you see, you have defined what ALU does for certain instructions or certain opcode specification. But if there are certain conditions, some situations where you which you don't care, so you in the output, but you have to define something for all cases of inputs, all possible input combinations.
So okay, can you go to the previous slide just once?
This one?
Yes, sir. So just a second, I wanted to see something.
Yeah, here I was showing D flip-flop which has synchronous set and reset. Okay, that means even initialization operations are happening with the clock. So if S is 1, then initialize to 1. If R is 1, initialize to 0. And you can see the condition you are checking first is overriding other condition. If S is 1, you're looking at R, you're not looking at anything else. Okay, only when S is 0, you look at R. If R is also 0, then you look at D and assign it to Q.
Sir?
So there is order in which you can. Yeah.
So suppose in this case, our D did not change. No, not in this case. Like in the asynchronous case, our D did not change in the combinational circuit. I mean, then what would Q be assigned? Like D would not get an undefined value. Like it would have that value, right? It's a register or a flip-flop kind.
The values are sustained in some sense. You don't change.
So your voice is lagging a lot.
Yes, sir, your voice is breaking.
Can't hear properly.
My connection. Just give me a second. Let connect. Okay. So you're still able to see the slides?
Yes, sir.
Okay. So is voice okay now?
Yes.
All right. So what I was saying was that a combinational circuit output does not change if there is no change in the input. Okay. But that can't be interpreted as storage. So between two changes of inputs, obviously the output will not change. In case of sequential circuit, the output could retain its value even if the inputs are changing. So for example, for a clocked circuit, if clock doesn't change, other inputs can keep changing. They don't cause any change in the output.
Suppose we have in input A, B, and we have an output where C is getting some some function of A and B, and A is changing, but B retains the previous value. So C would get the new value considering the old value of B, right?
Yes. Yeah. So it'll you will see what is the value of B at that instant. Okay. A gets a new value, and at that time, whatever is the value of B would combine with value of A and decide the value of D of C or whatever.
And that would be the original value of B, right? Then how is it like different? No storage memory. I don't get it.
See, B may be coming from another combinational circuit or a storage circuit. So if if B is not changing, it's the value of B at the instant of evaluation that will be taken. So whenever there is any change in any of the input, okay, one input may change or multiple inputs may change. That time you look at all the values of all inputs at that instant and decide the value of output. So in fact, that new computed value of output may incidentally happen to be same as the old value, but that is okay. A new value is computed and assigned to output.
Yes, I got it. Thank you.
Okay, so another issue is signals and variables.
So I had a doubt regarding processes on sequence. So do sequential circuits need to be in a process for them to be sequential? Can you say Q assigned to D when clock equals 1 and clock event, else?
Yeah, see,
Q.
you can use concurrent assignments also, basically conditional assignments to describe clock circuit, but it's fine. But a typical practice is to put that in a process. Okay.
Okay.
You have process sensitive to a clock, and right at the right in the beginning, you check for where the clock is having its rising edge or falling edge, whichever edge you want, and then make all the assignments you want. Okay. So signals interconnect processes, but variables are internal to processes. Variable is updated instantly, but a signal is updated after a delay. You could explicitly specify some delay, but if you don't, then it is assumed to be delta delay, which means that which is also 0. Okay, but it is you could think of this as infinitesimally small delay, or you could say that the value is available at the next instant, not at the same instant. So, for example, if you are making assignment to a signal on a clock edge, then the assigned value is available in the following period, in the next clock interval. All right, and the value you have assigned would have been computed from the old value, from the values which are available in the previous cycle. So that is where a cycle delay comes, right? So if you're saying A is assigned some expression, let us say B plus C, and this assignment is happening at a clock edge. So value of B and C are taken, which were available on that clock edge and before. Okay, so they would have been assuming that those values are also coming from sequential circuits which are synchronous. Those values would have been available for the entire interval, which is just before the clock edge, and also continuing for some delta delay after the clock edge. So that's as far as the inputs are concerned. Based on that, you compute the expression, make an assignment to a signal. So the signal will also get value after the clock edge, after some delta delay. And therefore it is available during the next clock period. Okay, so these were something I wanted to say about VHDL. Then I want to talk a little bit about the assignment also.
Sir?
Yeah.
So when signals are assigned in a concurrent assignment, let's say it takes place within a process, a sequential process. So if we assign some other value, let's say A is assigned B and D, and D is assigned A. So within the same process, D will get the old value of A, right?
Yeah.
But let's say after the end of the process, we have some concurrent assignments. So in that case, will A will have the updated value or still have the same old value?
So let me make it even simpler. Suppose you have a clock process, okay, and you say A assigned B, B assigned A.
Yes, sir.
And you have to write in some order, okay. You will say A assigned B semicolon B assigned A, right? You may put that order, but both these assignments will take place at the same edge. And the result would be that old value of B is assigned to A, old value of A is assigned to B, which means the two interchange their values. And the circuit which is outside this process will also see that before the clock edge, A and B had old values. After the clock edge, they'll have new values or interchange values. So this is exactly what will happen. Suppose in hardware, you take two registers, call them A and B. Output of register A is connected to input of B. Output of B is connected to input of A. And you clock them simultaneously. The result would be that their contents get interchanged. Okay, so unlike software where you need to have a third party, you assign A to temp, then temp to B and B to A and something like that. Of course, we saw that you can avoid use of a third location using XOR. You can interchange between, but you still require 3 steps. In hardware and also in clock VHDL processes, you can exchange on a single clock edge. Okay, so that is something you should keep in mind.
Sir, I still have a doubt in like asynchronous and this combination circuit. In flags, let's say what we have designed for flags, in that sometimes we say that we do not need to update V for some inputs, right? Let's say for test and all. So in that case, since it is being made combinational, how will we ensure that V gets its previous value? Because we are not updating V.
The flag V would be an edge triggered circuit. All the flags would be edge triggered circuit. The computation of values which are leading to these flags would be coming from combinational circuit. Okay. For example, output of ALU, you check if all bits are 0 or not. Okay. So the logic to check that would be combinational. But this would feed into a flag, Z flag, which is an edge triggered flip flop. Right?
Yeah, that is.
So you may when you clock it, it gets value which is computed by combinational circuit. When you don't clock it, combinational circuit is still producing a result whether output of ALU is 0 or not. Combinational circuit will always keep doing that. But that value may be stored in that, may not be stored in that, depending upon when you clock or when is.
So that flags entity, it should be clocked, right?
Yeah, flags will be clocked.
Okay.
Flags will be clocked. The logic which will compute the values for it will be combinational. Okay, so now in the next stage of the lab assignment, you are going from a single cycle design, which is something like this, where you had designed instruction memory, a program memory, register file, ALU data memory, and these were 4 components. PC together with all this input logic, all these both these adders, was designed as another component. And then there were the logic to decide what the flag should be and whether the condition specified in the condition field of instruction is true or not. Okay. So now going from this to multi-cycle design, let's see what are the changes. One change is that the 2 memories get replaced by a single memory. The adders also are clubbed with ALU. So ALU is supposed to do all the addition, subtraction, and all such stuff. So these are main changes. Okay, and of course the glue logic which is connecting all these is changing. There are a couple of more multiplexers. This multiplexer wasn't there, it is there now. This multiplexer at this input of ALU is wider, and there are some registers, IR, DR, A, B, and result. These are 5 additional registers which have come. So from, let's say, VHDL description point of view, we had these 8 components designed and instantiated, connected through glue logic, which was basically combinational in single cycle design. This whole thing is combinational. And my recommendation was that you write a couple of concurrent assignments for that. Concurrent assignments with condition or with selected signals. So this is taking care of all the multiplexers and control logic which is connecting the other components. Now going to multi-cycle design, there is change happening here. A single memory. PC is only PC now. All that adder stuff is being clubbed within ALU, so that is another change. There is change in glue logic, but here now you have what is called control FSM, a finite state machine, which steps through various cycles which an instruction requires. Plus we have these registers A, B, IR, DR, and RES, which need to be clocked. So I'm saying that this all could be one single process which is clocked, because these registers are also clocked. It will be convenient, although not necessary, but it will be convenient and more compact to put this as one clock process, and then there'll be some combinational circuit in the form of concurrent assignments, which will take care of the modified glue logic. Okay, some stuff may be same, some will get modified. The 2 memories could be clubbed, and the control FSM will have these 9 states. All the rectangular boxes which you see here would correspond to states, and wherever there are conditional transitions, I'm showing these through these diamond boxes or these hexagonal boxes. Yes.
Sir, here when we have a clock in the outside process, then the clock, it is not a single cycle, right? These will all take 1 clock cycles. First step, second step. So how do we keep it inside 1 clock?
Yeah. So in every clock cycle, the control FSM will go from one state to other state. Okay. So in the way you define FSM is that you look at the current state and take the action which is described in the box. So 2 things need to be done. One is, for example, look at this state. Okay. In this state, you will make some assignments to A and B, and also make an assignment to the control state register. You will go to this state or this state or this state, one of the 3 states, depending upon what the instruction is. So there'll be a big case statement which will look at what the current state is, and then accordingly you take some action. So it will be still a 0 time process. That means you take the action corresponding to one state only, and that action is taken in 0 time. So 2 parts of the action. One is, if any of these registers needs to be assigned, you assign something to that, and you keep the state in another signal which is actually implemented as a register. So to that signal you assign the new state. Okay, these 2 things have to be done. The changes required in PC is that now the logic for addition and sign extension is no longer required. ALU will provide the next address that goes into the PC. But you're not clocking PC in every cycle now. In the single cycle design, PC was changed in every cycle. So there was no write enable signal, but you need to now create a write enabled signal. So for example, going by this, this is one state where PC is changing, and this will be another state where PC will change. Here it will change conditionally if the branch condition is true. So now the question is, yeah.
So in the previous one, I think the diagram did have a PC write, which I just set to 1 always because, so we can just change that, I think.
Okay. Yeah. So PC will not be writing in every cycle. That is what is to be ensured. So computing next address instruction with ALU. So the question is, how do you do PC plus word offset, PC plus byte offset plus 8? So what I'm suggesting is that instead of byte address computation, we do word address computation. Then what we need to do is from PC, we look at only bits 2 to 31. That means, which is giving us the word address. And we take word offset. So now PC would have been incremented once in first control state. Okay. So you don't actually need to do PC plus offset plus 8. You need to do PC plus offset plus 4. But now thinking in terms of byte, in terms of word addresses in place of byte addresses, you need to do increments of 1 only. Okay. 4 and 8 were coming because you were talking about byte addresses. Now, this is something which can be done by ALU. ALU is geared towards adding 2 operands and a carry. So this one could be provided as a carry, and you could tell ALU to perform ADC rather than add. Okay. So ADC is add with carry. If you give the second operand 0, then this is what you do in first control state, and this one is what you do in case of branch instruction. Now ALU requires 32-bit addresses, 32-bit operands. So you take 32 out of 32 bits of PC, you are taking 30 bits. So you need to prefix it with 2 zeros. And similarly, the word offset field in the instruction has 24 bits. So you need to do signed extension of that by 8 positions. So add these with 1, then it takes care of next address computation.
So for doing add with carry, don't we need to change carry flag?
Your voice was not clear. Can you?
For doing add with carry, don't we need to change carry flag as well?
Yeah. So the carry input of the ALU will have to be manipulated. So when you are using ALU for this purpose, you make sure that carry input goes as 1. Okay. Okay, so this is all I had about VHDL in the lab part. Let's now get back to our usual stuff.
Sir, I had a doubt regarding the selection of the second operand in DP instruction. Okay. So it was mentioned that DP instruction could be either like immediate operand, or it could be register address. Yeah. So I had trouble deciding the control logic, how to decide whether either of them is present.
So basically you would need a multiplexer. For example, if you see on the screen, the ALU, the second operand is being fed by this multiplexer. Okay, so one input is coming from the register file, other is coming from the instruction with the suitable extension.
Yes, sir.
Okay, so this is the logic, this is the arrangement for choosing how the operand 2 is coming, and this would be the selection signal would depend upon whether instruction a certain field of the instruction will tell you whether you have to take register as an operand or immediate as the operand.
Okay, sir. So the I field essentially
I field
determines the immediate order.
bit of the instruction.
Okay, all right.
Sir.
Yeah.
Sir, in this, after this instruction is taken 11 to 0 bits from. So, sir, here we are taking that 7-bit offset also. So, how do we decide that which one of these has to be taken, and we have to also perform shift or that rotation in this?
Yes. So rotation will come into picture later. So let's forget about rotation right now. Right now, one operand is these 8 bits from the instruction, assuming there is no rotation, then it needs to be extended to make it full 32 bits. This is for DP instruction. Now for branch instruction, when you want to perform that offset addition, which is 24 bits and needs sign extension, you have another path for that, and the multiplexer will have to select between those paths. Okay, so maybe I can go back to this diagram.
No, sir, not about that signed offset. There are two kinds of offset. No, one is 8-bit and one is 12-bit. It becomes 12-bit after we add rotation to it. So.
Yeah, so all those options are not shown here. So you will have multiple inputs. I mean, this is not showing the circuit for entire set of instruction. What you are seeing on screen now is that there is a 12-bit part which is getting extended, and there is 24-bit part which is getting sign extended. Okay, so they are two different alternatives coming to the multiplexer and then getting selected. So you would need to deal with 3 things. For DP instruction, 8 bits are coming. For load store instruction, 12 bits are coming. For branch instruction, 24 bits are coming. So they need to be extended in different ways, and one of these will be selected. Okay, so now let's get back to pipeline design. So this is a 5-stage design we are considering, right? The details of what is there in each stage could vary depending upon instruction, but this is a classical 5-stage pipeline where first stage is instruction fetch, second is instruction decode or operand fetch from register file, third is execution through ALU, fourth is access to the data memory, and fifth is write back into register file. Okay, there are these registers which are interstage registers, and they typically get labeled in this manner. IF/ID means that it's a register which is interfacing IF stage and ID stage. Similarly, you have ID EX, EX MEM, MEM WB, corresponding to the 5 stages: IF, ID, EX, MEM, and WB. So we had seen a comparative picture of how different kind of designs are controlled. So for single cycle design, the control is through a combination circuit, which looks at the instruction and controls various other stages, various components.
Sir?
Yeah.
The one thing, so I had a doubt previously. So then the previous slide, P should come out of the flags, right?
Yeah, P should come out of flag. Yeah, so I mentioned that it should come out of the flag. Yes. So for Multi-cycle design, it's a control FSM which has some state, and the control signals depend not only on the instruction but on which step or which stage you are in. Okay. For pipeline design, sorry, we follow approach similar to single cycle design. That means all control signals get generated simultaneously, but they get applied with different delays. Okay. So since these signals are getting generated in second stage, when you already have the instruction, to this stage you apply directly to the ALU stage after 1 cycle delay, to DM stage after 2 cycle delay, and so on. Right? And these registers which provide delay could be considered as extension of those interstage registers themselves. So effectively what you would see is that anything which is going from one stage to other stage, be it data, be it control, passes through these walls. So these are like chambers separated by the walls, and control data, everything passes through these walls, getting delayed by 1 cycle and becoming available in the next chamber or next cycle. So to control these registers in view of hazards, we could have circuit something like this. So normally information keeps moving from one stage to other stage. Okay, every cycle everything shifts by 1 position towards right. Now to stall the pipeline, for example, you would need to control these registers which are separating one stage from the other stage. So here what I'm showing is that there are these gates, and the enable signals for these different stages are shown here. Okay, through these gates, if you, for example, if you keep 1, then that particular stage register clocks, and the information which was there then put moves to the next stage. Okay, so by controlling these, making them 1 or 0, you can enable or disable forward movement of an instruction at a particular stage. For example, here, suppose you disable clocking of these 3, PC, this IF ID register and ID EX register, but you enable the other 2. What will happen is that since these registers are clocking, they will get the next input and make it available to the next stage. So whatever was happening in ALU stage, the result get stored in this and are available for the next stage. Similarly, whatever happened here, those results are clocked into these registers, this register, and they are available for the next stage. But if you are not clocking these 3 registers, then they remain static. That means PC does not increment, new instruction doesn't get fetched, new operands don't get fetched. Okay, so effectively, the instructions which were in previous stages get stalled, whereas the instructions in which were in these 3 stages, they move forward. Okay, so depending upon at which point you want to stall, which stages you want to, which instruction you want to stall, you can enable or disable these signals. And there is, so when you stall, for example, you are not having the information moving from RF stage forward to the ALU stage. Okay, because this register is not getting clocked. So we need to introduce bubble. So here it is showing that you can have the normal signals, or let's say all zeros. You could select one of these and clock that. Okay. So assuming that, so I'm showing it for control signals here. Assuming that control signals are such that 1 means active and 0 means inactive, or 1 means enabled, 0 means disabled. So any control signal which are going to the next stage, they are made 0 if we allow the lower input of the multiplexer to go through. So this is like introduction of bubble. That means all inactive control signals will go and instruction will be like no operation, not doing anything. Another issue was that for data forwarding or for data hazard detection, we need to check dependence among instructions and accordingly control the data forwarding logic. So the condition which needs to be checked is, for example, shown here, that operand of instruction in the RF stage is a register in which instruction in the ALU stage or DM stage is going to write. Okay, it is the RF stage or the second stage when an instruction is reading operands. And if these operands are yet to be written by instructions which are ahead of this instruction, then that's a hazard condition. So the instruction which is supposed to provide the value in RF is still in ALU stage or in DM stage. Right, so that's a hazard condition. And the way we could check is that we can look at the control signals as they are available in these interstage registers. So let us say RW is a signal which enables write into register file. Okay, so ID oblique EX dot RW equal to 1 means that instruction which is in EX stage, okay, the register between ID and EX stage is ID oblique EX, and dot RW means the RW signal as latched into that register. So if that is 1, it means that the instruction in this stage is something which is going to write into register file. And this check, that means instruction which is in the ID stage, its RN component is equal to RD component of the instruction which is in EX stage, or RM. So either RN component or RM component of the instruction in ID stage is matching the RD component of instruction in EX stage. Right. So what we're saying is that instruction which is in ALU stage or EX stage is going to write into a register that is RD that matches with the source register, the operand register of instruction which is in RF stage, or same name, ID is the name of same RF stage. So this is one possible condition. The other part was that instruction which is writing could be in DM stage. Okay, so we check EX oblique MEM register, same field, the same condition, but in place of ID EX we have EX MEM register. So if either of these condition holds, then there is a hazard, and depending upon whether first condition holds or second holds, we'll enable appropriate data forwarding path 1 or 2. Okay.
Sir?
Yeah.
Here do we also have to check if the instruction is something like move, where you only need one operand, only one register, so you might not have to stall?
Exactly. Yes. Yeah. So if instruction is not looking, so here we are imagining that if any of the operand is dependent upon a previous instruction, then there is a hazard. But if it is instruction which takes only one operand, like move or move in, then the other check for the second operand sorry, it takes only second operand, not the first one. So Rn part is immaterial. Therefore, in a more refined sense, this check also would depend upon whether the instruction needs 2 operands or 1 operand. Yeah. So in fact, so I've qualified that here. We need to ensure that instruction RF stage actually reads Rn and or Rm. So we have not taken care. So we need to look at instruction whether it needs Rn operand or Rm operand both or one of these. Okay. So pictorially, what we are trying to do is we are imagining that the instruction which reads register file is in this stage. I'm calling it reader instruction, and writer instruction is in this stage. Okay. So the control signals for reader instruction or instruction which is in this stage are there in this register. And control signals for this stage are in this register. So that is how we were checking. So when we say if oblique id dot rn or if oblique id dot rm, that means we are looking at these values as present in this stage. And id ex means that we are looking at this register. So that pertains to the writer instruction. This is one possibility, reader here, writer here, or other possibilities, reader here and writer in DM stage, and therefore the check is correspondingly made different. So now the paths need to be enabled accordingly. The path going from this point back to the ALU inputs is called path 1. Path 2 is coming from the next stage, that is this one, and coming back to ALU inputs. So we saw it as this ALU to ALU transfer, and the control signal forward A is 0 would select the operand coming from register file. 1 is selecting the operand coming from forwarding path 1, and 2 is selecting the operand coming from forwarding path 2. So if forwarding a control signal is 1, if this condition holds. Okay, so here we are matching Rn, and forwarding path 2 is coming from output of DM stage to ALU. Here we need to imagine that reader is here and writer is here, and there is no writer in this, because if this is the writer, if there is a writer here for that same register, then this will overwrite what this one does. Okay, so we need to check absence of this also. And here is the complete condition for making forward a signal as 2 to enable path P2. We check for writer. Just a minute, I think I should. Okay, so what we are checking is that the destination of this one, destination of instruction which is in WB stage, is matching with the source of instruction in the EX stage. Okay, and is not matching with this. So that means if instruction which is here in memory stage, it writes in maybe a different register, does not write in the register which this one is trying to read. So that is the condition for path P2. Path P3 is from DM stage to RF write stage. So here we have to enable path going from here to here. So I'm calling this control signal as forward C. Forward C is made one if you have writer here and a store instruction here. Okay. So store instruction is the one which is reader. So this is for the writer. Okay. And the RD field of this is matching with the RD field of this. Right. Now, if you have a writer here and a reader here, then you may still need to stall. So this is the case when you have. Let me show you. So in forwarding from this stage, if the okay. Yeah, so suppose you have load instruction which is getting its data here, and it needs to be forwarded to a DP instruction. Okay, so if DP instruction is following immediately, it will have to wait for one cycle to reach in this position where it can get the data from load instruction. So the condition for that is being checked here, that you have a load instruction which is in this stage yet. Okay, so it is still not prepared to forward the data here. Only when it reaches in the next stage, it can forward the data, and therefore this has to be delayed. This waits here. It cannot go to ALU stage. Only when LDI instruction reaches this stage, then it is possible to forward the data. Okay, and it can move to the next stage. So the condition for this is that the instruction in EX stage has its memory read signal as 1. Okay, that may this is a signal indicating that this instruction reads from memory. It's a LDR instruction, and the RD of the destination of this load instruction is matching one of the operands of instruction which is in the EX stage. So this is a condition for stalling. That means we'll hold this instruction back, let LDR instruction move to this stage, and then the data gets forwarded through path P2. Okay, that is all for today.
So can you once again explain the previous condition, like stalling bit data forward?
Okay, this is indicating the condition under which an instruction which is reading from some register needs to be stalled. So imagine that this instruction, let's say a DP instruction, is an ID stage. Okay, normally it would have read data here, but data is not available. So we would expect that when it reaches the next stage, the data will get forwarded to it. But LDR is not able to forward the data at the end of the cycle. So we need to stall this. LDR instruction has to move to this stage before we can forward the data. The condition for that is we are checking that the instruction in EX stage is a memory read instruction or load instruction, and the instruction in ID stage has its RN or RM value matching the RD value of the instruction in EX stage. Okay, so under this condition, we will generate a stall signal for the pipeline to hold this instruction back within ID stage. This instruction will not be held, it will move forward. And when it reaches here, that condition for data forwarding through path 2 will be valid and the data will be forwarded. All right. So
Sir, I had a doubt in the VHDL thing. So can you just show that file in which you showed the VHDL?
Yeah.
Yeah, in this one, the flip-flop synchronous one.
Yeah. This one?
Yes, sir. So suppose I wanted that, I said that D might be changing at the clock edge. So if I designed it in this way that the process contains clock and D, and then the other part remains same, because we are still checking for the rising edge of the clock. So by doing clock equal to and clock event. So is there any problem with this design?
So actually in this design, you see the outermost condition check is the clock edge check. Right. So just for the sake of argument, suppose in the list of the signal sensitivity list, I include S, R, D, everything I include. So if I put those extra signals, it's not going to make a difference, because suppose there is a change in D. You enter the process, find clock edge is not there, do nothing and come out. Suppose there is a change in S. You enter the process, find there is no clock edge, you come out. So if you're checking clock edge at the outermost level, that is the first condition. If that doesn't hold, any other change will not cause any effect.
No, sir, I mentioned that issue that my D was changing at clock edge. Okay. So suppose so it is changing at clock edge. So when a change in D is made, I wanted that the new.
Let's not imagine that clock and D are changing simultaneously. So practically, let's assume that all asynchronous signals have been synchronized, and when you get to this point, D is changing little after the clock. So imagine that situation.
Okay, so till now the VHDL design that I wrote, in that everything was changing at the clock edge only.
Yeah, so everything, when you say everything changing on the clock edge, it means that the change in other signals will appear after some delta delay after the clock edge. So any other circuit will see those signals changing, not exactly at the clock edge, but after the clock edge. So you need to understand this cause-effect relationship. Clock edge is the cause, and change in any signal is the effect. So effect is after the cause.
Okay.
Yeah. Okay.
So I have a request to make. Yeah. So as you know, the stages, the forthcoming stages will be